problem. Okay, so in this problem, we are shown a rotating load, a rotating shaft that is machined from AISI 1020 cold drawn steel. Okay, subjected to force 6 kilonewton, and find the minimum factor of safety of fatigue based on infinite life. Okay. So we have to find the fatigue factor of safety if the life is infinite. If the factor of safety turns out to be less than 1, then we can uh, check for calculate for number of cycles. So where to start? कहाँ से start करें? So first, once again, understand that because this is a pure bending problem, so you are given you are not given any torques or things like that. Okay? So it's a pure bending problem. Okay? And also the load, the stresses that are produced would be complete as the shaft would rotate. The stresses would be completely reversed. Okay? So as I talked just now, so this falls into the criteria for which we can solve the problem. So what should be the first step? So we can stresses. So stresses को पहले discuss कर लेते हैं. पहले strength part कर लेते हैं. Strength part is the easier part we have been doing. So obviously there are two parts to this question. One is the strength part where you calculate the actual strength of this shaft endurance limit, and other is obviously the stress part. So we will come to that later. So starting with the strength part, we have been given 1020 cold drawn steel. So again, going to table A20, we can find its ultimate strength, that is 470 megapascal. Okay. And then endurance limit for test specimen would be 0.5 SUT. And remember this, what is the limit of applying this formula? Limit for applying this formula. Can it be applied to any SUT?
Less than 200. 1400.
SUT up to 1400. 200 नहीं यार, 1400. ठीक है?
जी सर.
KSI को इग्नोर रखें यार. SUT ये मेगा पास 1 यूनिट भी हो जाए तो बहुत बड़ी बात है. ठीक है? So SUT 1400. After that, whatever SUT is, maybe 1600 or 1700, you would take SE prime is equal to 700 megapascal. ठीक है? So SUT for this case comes out to be SE prime comes out to be 235 megapascal, and then there are the factors that allow you. So this is our estimate for the rotating beam endurance limit of the rotating beam test specimen. So now we come to the R part. So what would be the strength of this part? So that would be SE when we have to multiply it with these endurance limit modifying factors. So are we given any information about the surface finish?
सर मशीन है.
Machined cold drawn surface finish point of view, the same result. So surface finish equation is ASUT and remember these A and B are different from another A and B that we have also read in this chapter. Okay? So this is a different equation. These A and B are different, and these A and B are different. So don't confuse these two. Okay? So this you'd see in table I think 6.2, that is 4.51. SUT would be 470 and B is minus 0.265. Okay. So that would give you the surface factor as 0.88. Okay. What about the size factor? So because this is a pure bending case, so we don't have to find and the shaft is rotating, so same as our original specimen. Okay. So which equation to use? चले इक्वेशन तो हमने यही यूज करनी है. Which diameter to use?
35.
Why?
क्योंकि ये रेडियस से सब बिलो है. जब हम रेडियस ऐड करेंगे तो कैपिटल डी हमारे पास आएगा वो 50. ग्रूव से बिलो है.
नहीं मुझे समझ नहीं आई बात.
सही है. रेडियस से बिलो है जो
किस रेडियस से?
3R.
हाँ नहीं तो ये 25 क्यों ना ले लें?
सर वो बियरिंग का है आई थिंक.
नहीं बेरिंग का है तो वो भी शाफ्ट का पार्ट ही है ना. यहाँ पे बेरिंग माउंट होगा बट शाफ्ट का पार्ट तो है ही.
हमने शायद रेडियस से पास लेना है.
नहीं हमने क्यों शायद लेना है रेडियस के पास है.
सर मेरा ख्याल है मिनिमम लेंगे क्योंकि वो वीकेस्ट पॉइंट होगा.
मिनिमम लेंगे या वीकेस्ट पॉइंट होगा? ओके. एनीबॉडी एल्स? Okay. So, so we cannot calculate KB at the moment because KB would be different for this part, would be different for this part, would be different for this part. Okay? And obviously we have to compare our stresses with strength, but stresses we know that the stresses would vary throughout this shaft. Okay? Stresses would vary throughout this shaft because what are the stresses in this shaft? These are the bending stresses. Okay, so bending stresses depend upon the bending moment, and bending moment is changing throughout this shaft. Okay, so our enterprise is doomed before calculating the stresses because first we have to identify which is the critical point in this shaft about which we want to calculate the stress and solve this problem. Okay, so first we have to identify that. Without that, because we don't have a computer would calculate the stresses at all points and then the strength also at all points and compare at all points, but we can't do that. Okay. So first we have to identify the critical points on this shaft at which we would calculate the stresses. Maybe we can directly identify one point, or maybe we are unsure about 2-3 points. So then we would have to solve for 2 or 3 points. And then we would calculate the strengths differently for those 2-3 points. Okay. So we would stop here the strength part, and then we can start with the stress part here, so that we can compare the first identify the critical point. So how will we identify the critical point on this shaft?
बेंडिंग मूवमेंट डायग्राम से सर. shear of bending.
Okay, so first we would have to draw the shear moment diagram and then obviously the bending moment.
सर फिर रिएक्शन आएंगे ये 25D के ऊपर?
बिल्कुल रिएक्शन आएंगे. ठीक है. So you would have obviously.
तो ये बेयरिंग का डाया है या शाफ्ट का ही डाया है?
ये शाफ्ट का डाया है जिस पे बेयरिंग अटैच हुआ. ये शाफ्ट कट आया, बेरिंग की इंफॉर्मेशन नहीं दी हुई, ठीक है। यहाँ पे मैं बस ये बताया यहाँ पे इस पॉइंट पे बेरिंग अटैच हो,
ठीक है सर।
सो फर्स्ट ऑब्वियसली अगर मैं इनको पॉइंट ए और सो इस पॉइंट को बी कह देते हैं, इस पॉइंट को सी कह देते हैं, और ये लास्ट जो पॉइंट है इसको डी कह देते हैं।
सर बेयरिंग लोड को फिक्स पोर्ट लेंगे?
बिल्कुल फिक्स लोड लेंगे। सो फर्स्ट ऑब्वियसली एफ में दिया हुआ है, ठीक है। सो यू हैव टू फाइंड दीज रिएक्शन फोर्सेस। So reaction, I think you can do that. So we are not going to. So RA would be 2.1 kilonewton. RB. So looking at the figure, it's clear that RD would be more than RA. ठीक है. So first step you would have to perform would be to find the reactions and then draw the shear force diagram. ठीक है. So shear force diagram would be something like this, and then from the shear force diagram we can draw the bending moment diagram. ठीक है. So bending moment would be, diagram would be like this. So M max would be occurring somewhere here. ठीक है. So now can we identify from the moment diagram, looking at the shape of the part and the moment diagram, can we identify the critical points?
सर हमारा सी वेरी कर रहा है इसमें, तो इससे तो नहीं पता लगेगा खाली।
सी वेरी कर रहा है मतलब क्या कह रहे हैं?
सर जब हम अलोंग द शाफ्ट देखेंगे तो कुछ एरियाज पे हमारे पास रेडियस कम है, मैक्सिमम कुछ पे ज्यादा है, तो सिर्फ मैक्सिमम बेंडिंग मोमेंट से तो नहीं हम ये कह सकते कि यहाँ पे क्रिटिकल पॉइंट है।
हाँ तो मैं यही कह रहा हूँ, तो वी हैव टू लुक एट दिस शेप एंड द बेंडिंग मोमेंट डायग्राम।
जी सर।
तो कौन से क्रिटिकल पॉइंट हो सकते हैं, मतलब ऑब्वियसली एक तो कंटेंशन में कौन से पॉइंट है, एक तो ये पॉइंट है वेयर द मोमेंट इज मैक्सिमम, और कोई पॉइंट?
सर पॉइंट बी जहाँ पे नॉच आ रहा है।
पॉइंट बी, बिल्कुल पॉइंट बी देयर इज अ स्ट्रेस कंसंट्रेशन या स्टेप है, ठीक है। सो हियर point B is also could be critical depending upon the stress concentration, and point D, point C also has the step, so it could also be there. So this point obviously, this point they would usually have very low moment. So I think most probably if you look at it, it's clear that the either this would be the critical point or this would be the critical point. Just for comparison, we can see about what is the situation at C also, okay? But most probably these two are the critical point. Okay? So if we go for a max, okay? So maximum moment, obviously force is given, so the distance is given, so calculating the moment at this point is not very difficult. Multiply this this distance, so you get 682 kilonewton millimeter. Whereas the moment at point B is this 2.1 multiplied by this distance, that is maybe 200. Okay? So turns out to be about 420 kilonewton millimeter. And just for comparison, we can draw the moment at point C, because point C also has a step. So that is only 78 kilonewton. Okay. So now looking at this, okay. So if you compare these two, okay. So moment is the maximum at this point, but this point has large diameter. So diameter is 50 millimeter at this point, compared to point B, where the diameter is only 35. Okay? And also no stress concentration factor. Okay? So this point also does not have any stress concentration. There is no step change. Okay? So what do you think is the critical point now? Is it obvious? हाँ भाई, कोई ऑब्वियस नजर आ रहा है या नहीं? याद?
यस सर।
कौन सा पॉइंट होगा क्रिटिकल पे?
सर 420 होगा फिर, लेकिन
हाँ।
मुझे लॉजिक नहीं है समझ आ रही।
लॉजिक क्यों नहीं समझ आ रही?
सर वो 682 मैक्सिमम है,
बिल्कुल।
लेकिन हम यहाँ पे 420 ले रहे हैं।
हाँ, बिकॉज देखिए ना 682 पे डायमीटर भी ज्यादा, एरिया भी ज्यादा, ठीक है, आई भी ज्यादा होगा।
जी सर।
ठीक है
जी सर।
और वहां पे स्ट्रेस कंसंट्रेशन भी कोई नहीं है। ठीक है, तो जब आप स्ट्रेस कैलकुलेट करेंगे तो, और यू कैन कैलकुलेट मैक्सिमम स्ट्रेस, वो तो कोई मसला नहीं, आप उसके लिए भी कैलकुलेट कर लें। इस पॉइंट, जब पॉइंट बी के लिए करेंगे तो यहाँ पे आपके पास के एफ भी है, ठीक है, और ये भी एरिया भी कम है, ठीक है, जबकि ये जो पॉइंट है, अगर इसको ई कह लेते हैं, ठीक है, सो इस पॉइंट पे देर इज नो स्ट्रेस कंसंट्रेशन फैक्टर, ठीक है, सिर्फ एम वाई ओवर आई, और एरिया भी ज्यादा है, ठीक है। सो अभी अगर इट वुड बिकम मोर क्लियर व्हेन वी फाइंड द स्ट्रेस कंसंट्रेशन फैक्टर, बिकॉज स्ट्रेस कंसंट्रेशन फैक्टर भी यूजुअली 1.52 के अराउंड तो होगा, ठीक है। सो स्ट्रेस कंसंट्रेशन फैक्टर जब फाइंड करेंगे तो वो इतना तो डिफरेंस नहीं है इनके मोमेंट्स के दरमियान में, ठीक है, और फिर एरिया का भी डिफरेंस है, ठीक है। तो मोस्ट
जी सर।
प्रोबेबली we can see that the stresses would be higher at this point. This would be the most critical point. Otherwise, you can calculate that. Okay? If you are not sure, then you can calculate the maximum stresses and compare. ठीक हो गया?
जी सर।
चलो. So let us take the assumption that point B is the most critical, and move forward, and then when we find the stress concentration factor, okay, so it would become more obvious, I think. Okay. So so first, if we just find stresses find करें, या चलो पहले stress concentration factor find कर लेते हैं. Kf is equal to 1 plus Q Kt minus 1, ठीक है. So KT for this case, ठीक है, again you have to look at the appropriate table, ठीक है, A15 appendix में, ठीक है, that deals with bending, pure bending of a shaft, ठीक है, and for R by D ratio of in our case the R by D ratio, the radius is 3 and the diameter is 35, so R by D ratio would give you 0.08 and the other thing that matters is the step size, ठीक है, so D by D ratio, so step is at point B, so we are discussing what is happening at point B, ठीक है, so D by D ratio is 1.4. So for this R by D ratio and this D by D ratio, the KT turns out to be 1.7, ठीक है, and then we have to look at the notch sensitivity. So notch sensitivity for radius 3 and SUT 470, ठीक है, so for radius 3 this is 400, so 470 would be near this point, ठीक है, so Q would be, I don't know, maybe 0.78, something like this. So again, you don't have to be too precise with this. The thing that you have to show is that you need, you know which chart to look and where to look at on that chart. So that gives us KF as 1 plus 0.78 into 1.7 minus 1. So that would give you 1.55. Okay. So now, if you only take the effect of stress concentration factor, this moment is basically as dangerous as this moment. Okay. So the moment are, you can say, for equal, but here you are dealing with the smaller dia, here you are dealing with the larger. At this point, you are dealing with the larger dia. Okay. So again, I think there should not be now any confusion that point B is the most critical point. Any question until now? So now we can find the fully reversible stresses by using Kf, M, Y, what? I, so that give you 1.55 and 420 into 10 to the power 3 multiplied by Y 17.5 and I would be 5 by 4 17.5. So that would give you the maximum stress of about 154.6 megapascal. So that is the stress part. Okay? That are the stresses at most critical point. Okay? And now we move to the strength part. Okay? So we were stuck with this size factor. Okay? So now we know which point we are calculating for. So we are aiming for point B. So that means that diameter at this point would be 35. And that would give you the size factor of 0.85. Okay. Load factor. So what would be the load factor for this case?
1 over.
1 over. ठीक है, because we are dealing with bending, so same as the rotating beam test, we don't have to take into account the difference in load. ठीक है, and KD, KE and KF, because we are not given any information about the number of the temperature or the reliability difference or any miscellaneous effect, so we can safely take them as 1. ठीक है, so that would give us the SE of 176 megapascal. So that means our safety factor for fatigue is 176 divided by 154.6. That means 1.14. So we are still in the infinite life regime. ठीक है, so had this been less than 1, ठीक है, so then obviously we would have to find the number of cycles using that equation. ठीक है, so then we can use this sigma reversible is equal to SF. So for the what would be the fatigue strength is the for that sigma reversible, and that would give you the number of cycles. ठीक है, and lastly we are also had to check for yielding. So be sure to check for yielding. So we will do that. So SY again from table A20 we have to look for SY. So SY is about 390 megapascal. ठीक, so yield safety factor is much higher. ठीक है, it is about 2.5. ठीक, so it is much higher. So we are far from yield, but not much safe from fatigue. So maybe as a designer we can increase this safety factor if we have to design this part. So any questions from this? Okay. So now we have completed the fully reversed part, fully reversed loading in the stress life method. We know what to do when the loading is completely reversed. Okay. So all of our discussion until now was for completely reversed load, as is was apparent in the last problem. Now the two things remain. One is when there is a combination of bending, torsion and axial loading, okay, what to do then, and when the load is not completely reversed. Okay. So combination of axial bending and torsion we would see later. So now we would look at what to do when the loading is not completely reversed. Okay. And the generic name for that case is fluctuating stresses. So in a completely reversed load, the sigma max and sigma min magnitude was exactly equal, okay, and their direction was opposite. Okay. So what is the fluctuating load? Fluctuating load is any load in which this is not the case. Okay. So for example, it could be like this, okay, sinusoid, okay. Now sigma max is not equal to sigma min, okay. So for any case in which we have this, it could be like this also, and could be like this also, okay. So all of these cases in which the sigma max is not equal to sigma min are in the domain of fluctuating stresses, okay. So first we see how do we characterize the fluctuating stresses. So we characterize fluctuating stresses by two main terms, okay. Two main terms, that is sigma mean or the mid-range stress, that is sigma max plus sigma min divided by 2, okay. And the other term is sigma a, okay. And that is called alternating stress, okay. That is sigma max minus sigma min divided by 2, okay. So these are the two main terms that we would use to characterize the fluctuating stresses. Okay. So if we look at this case that we have solved previously for the rotating beam bending test and all the cases of completely reversed load. So here you can see that sigma m for this case is 0. Okay. So we didn't use this term, the mean term, but all of these cases, uh, easily looking at all the problems that the forces were from plus 10 to minus 10 or plus 28 to minus 28. Okay. So that means the mean force was, the mean load was 0. Okay. So this characterized all those cases. Okay. And so if we look at the figure, so this is sigma A. Okay. Sigma max minus sigma min by 2. This is also sigma A. So this sinusoidal pattern, that is the characteristic of most rotating machineries. Okay? Most rotating machinery, the load is changing in some sinusoidal pattern. So in fluctuating stresses, now sigma m is not 0, but maybe some positive value or maybe some negative value. Both are in the domain of fluctuating stresses. So this would be this value would be sigma mean, and this value is sigma a. Okay. So we would be using these two terms generally to characterize the fluctuating stresses cases. Okay. So what are some of the common cases? So one of the common cases is this, where the sigma mean is positive. Okay. Another could be like this, where the sigma m is negative. Another case is something like this, where we can say this sigma minimum is 0. Okay? And this is also called the repeated stress case. So sigma m is positive, okay, but sigma minimum is 0. Okay? So that is the repeated stress case. Okay? Now, any questions from this? Okay? So we have just talked about how to characterize fluctuating stresses. Okay? We use the term sigma mean and sigma A. Now, obviously, not all loads are like this. Okay? They are not all loads come in this beautiful pattern, you can say, of sinusoid, and that can be easily analyzed. Okay? So real loads obviously can be different from this. Okay? So for example, one common difference is that your main load is like this, but there's also a high speed ripple, okay, due to vibration or similar effects. Okay. Or another type of load could be where you have a pattern like this. Okay. Now, the question is, will our discussion about the fluctuating stress that we would be using sigma mean and sigma A, and mainly looking at the sinusoidal pattern, is that discussion applicable to these cases? Okay. And the answer is yes, because experiments have proven, okay, that it is not the exact shape of the or exact pattern of the stress chain, but the maximum value of the stress and the minimum value of the stress that determines the fatigue crack growth. Okay. So in both these cases, okay, we can, by using the same value for maximum and minimum stresses, we can approximate the behavior using the sinusoidal pattern. Okay. So our discussion that we would be having mainly using sigma m and sigma A to characterize the fluctuating stress is still applicable to these kinds of loads. Okay. So these loads are also in the domain of fluctuating stresses. Okay, that we would be discussing. Now, there is another kind of loading that is generally called service equipment loads, and these are the loading on the, you can say, the vehicles, the tire, the body की अगर बात करें, या ships, aircrafts हैं, where the load is variable over time. Okay? So there is no set pattern to that variation. Okay? So, so it could be something like this. Okay? So again, depending upon the wind speed and storms, okay? So we are talking about maybe ships and aircraft and things like that. So stresses on the structure, main structure of the body is changing with no set pattern. Okay? So can we approximate these kinds of stresses with sinusoidal method? No, we cannot. Okay? For these kinds of stresses, we use the cumulative fatigue damage method using generally either the strain life method or
इस तरह के स्ट्रेसेस होते किस तरह के, किसी स्ट्रक्चर पे तो इस तरह के स्ट्रेसेस नहीं होते।
बिल्कुल ये स्ट्रक्चर पे स्ट्रेसेस बताए हैं। ठीक है, ये जैसे कि एयरक्राफ्ट में हो सकते हैं, इस तरह एयरक्राफ्ट विंग है ठीक है। सो अब ये दे डिपेंड अपॉन द वेदर, ठीक है। सो अब उसमें मॉडरेट वेदर है, स्टॉर्म है, माइल्ड वेदर है, हाई विंड्स हैं, तो वो स्ट्रेसेस चेंज हो रही हैं, ठीक है। इसी तरह ये देखें, जो टर्बुलेंस है वहाँ पे स्ट्रेसेस बिल्कुल डिफरेंट होंगी, ठीक है। तो स्ट्रेसेस आर मच मोर वेरिएबल, ठीक है। इसी तरह व्हीकल की ज्योमेट्री, अगर इंजन की बात करेंगे तो वहाँ पे तो रोटेटिंग मशीनरी है, साइनोसाइडल किस्म की स्ट्रेसेस है। बट अगर व्हीकल के मेन शासी की बात करेंगे तो शासी तो डिपेंड करता है ड्राइवर के ऊपर, ठीक है ना, कि उस पर किस तरह की स्ट्रेसेस हैं। सो दे आर मच मोर वेरिएबल।
ओके सर।
ठीक है, बात के लिए। सो ऐसे इन केसेस के लिए वी यूज स्ट्रेन लाइफ मेथड और एलईएफएम जनरली, ठीक है। सो डायरेक्टली द साइनोसाइडल मेथड इज नॉट एप्लीकेबल, ठीक है। बट ऑल फॉर रोटेटिंग मशीनरी and even if the is like this, even the stress change is like this, still the fluctuating stress or the sinusoidal method that we would discuss would be applicable, okay. So now before moving further, let us just see some other terms, okay, that are used in fluctuating stresses. Mainly we would be concentrating on sigma mean and sigma A component, the alternating component of the stress and the mean component of the stress, okay. But there are some other terms such as the range of stress. So this is the total from sigma max to sigma min, ठीक है। इसी तरह स्ट्रेस रेशियो है, ठीक है, सो दैट इज सिग्मा मिन डिवाइड बाय सिग्मा मैक्स, ठीक है। यू हैव द एम्पलीट्यूड रेशियो, ठीक है, दैट इज सिग्मा ए बाय सिग्मा एम, ठीक है। सो दीज आर सम ऑफ द टर्म्स ऑफ, फॉर एग्जांपल एम्पलीट्यूड रेशियो, यू कैन से if the ratio is high, that means that the alternating component is dominating the stresses. If the ratio is low, then you can see the mean component or the mid-range stress component is dominating the stress cycles, ठीक। But mainly we would be concerned with these two terms, that is sigma m and sigma a. So So now, what to use, what to do when there is a combination of mean and alternating stress? That means there are fluctuating stresses present, okay. First thing that should be clear is that we cannot directly use the SN curve, okay, that we studied previously, okay. So SN curve obviously comes from the rotating beam test. So what is the mean stress there? What was the mean stress in this case? What was the mean stress when we are performing the rotating beam test? What is the mean stress? बिल्कुल, mean stress was 0, ठीक है। Obviously we were lying on a pattern like this, ठीक है। And this value of S, ठीक है, the stress value that we called sigma reversible, so for example, basically was the value of sigma A, ठीक है। So these values are values of sigma A, ठीक है, the alternating component of stress. Now at the moment we're just going to assume that we don't know the method of how to design with combination of mean and alternating stress, and we are faced with a problem in which there is some mean stress present. Okay? So we can maybe come up with our own method. Okay? So and then you see how much correct it is. Okay? So what do you think? So this was curve for sigma mean is equal to 0. Okay? So now what do you think will happen when sigma m is some positive value? What would be its impact on fatigue? And remember that fatigue is a basically tensile phenomena. Okay? It's most related to tensile stresses. Okay? Because we are talking about a crack growth, and crack growth needs tensile stresses to grow. Okay? So fatigue is a phenomena that is related to tensile stresses, is most concerned with tensile stresses. Okay? So when there is some permanent tensile stress present in the structure, apart from the alternating component, there is an alternating component, but there is also some. So we are talking about, so for example, case like this. Okay. So in this we have some sigma m positive value all throughout the cycle. So what would be its impact on fatigue life? What do you think? Will this improve the fatigue life of the material, or will it reduce the fatigue life of the material, or a part?
Improve.
सर ड्रॉप होगा क्योंकि टेंशन में होगा ज्यादा.
So intuitively we can guess. At the moment we can't know until and unless we perform some test. But for sigma m as some positive value, the fatigue strength should drop. Okay? And we should expect maybe a curve similar like this, but on the downward side. Okay? Whereas when sigma m is negative, okay, that means it is compressive. Okay? So then, because we have already learned about the residual stresses. So for example, when you have compressive residual stresses, then that is generally beneficial for the fatigue life of the material. Okay? So we can expect that when you have a mean stress that is compressive, to have some positive effect. Okay? And we will look at the test result later to see what would happen. But at the moment, we can maybe guess that this should happen. Okay. So now, if I want to draw a graph like this, where on one axis you have sigma a, other axis you have the sigma m. Okay. So, and I'm doing this for infinite life. So what is the sigma a for infinite life? So first we will discuss the case when sigma m is 0. Okay? So sigma m is 0. So on this graph we are at this line. Okay? There is only sigma a present, that is fully reversible stress. So for infinite life, what is the limit for sigma a? For infinite life, what is the limit for this stress for any material? What is this limit? Limit for this stress. How high this stress could be in terms of strength? क्या limit है इसमें? Point
The
कौन सा
less
है?
than endurance.
Endurance limit. ठीक है? So you have the endurance limit here, SE. ठीक है? So if the mean stress is 0, we can stress the part up to SE. Okay? The alternating component could be equal to SE. Beyond that, you will not have infinite life. Okay? And when there is no stress present, no alternating component present, so now what happens for this case? So when sigma A is 0, so there is no alternating component, only a static. So that makes it a static stress. Okay? Because sigma A is 0. So what is the value of sigma m? Basically, this is we are using the word sigma m, but this basically becomes static stress. So what is the limit for static stress where it fails?
सर yielding point.
यील्डिंग, बिल्कुल यील्डिंग भी हो सकता है, और इस केस में बिकॉज वी आर कंपेयरिंग इट विद फटीग, so fatigue is basically because fatigue is a fracture phenomena. Generally we don't talk about yielding related to fatigue, we talk about SUT. So we use this as our limit, that is SUT. So this is the point at which the material fails if there is no material fractures. Because at this point material fractures, as if your stress is more than endurance limit. So it's the same fracture point we have here. So then when SM is equal to SUT. Now for any sigma m as positive value, so for any sigma m as positive value, so there is some positive mean stress present. So we also previously discussed it here in the SN curve. So that means the life would be reduced. So we can expect a life to be somewhat lower than SE. Am I right? It's not very we can easily say that for any SM that is positive, the limit for alternating stress for infinite life would be less than SE. Obviously we don't know the exact point, but we can say it would be lower than this point. And as we increase it, it should be even lower. So the most crude, without knowing any experimental data, the most crude design that limit that we can come up with is joining these two points. So if you don't have any data and you don't know how to combine these mean and alternating stresses, so we can still intuitively, it is clear that at least this could be one criteria where we say that as we increase sigma mean, the alternating stress component must be decreased for infinite life. And higher the mean component is, lower the alternating component could be. Now if we look at, now let's look at the experimental data. What does the experimental data say about the combination of mean and alternating stresses? So again, this axis is the mean stress and this axis is alternating stress. And this is the same point. This is SE and this is SUT. It's just has been normalized by dividing it with tensile strength, so you get the value 1. But don't be confused by that. This is just SE and this is SUT. And if we see the failure points, from experiments, you can see first, obviously, as a characteristic of fatigue data, you can see there is a considerable amount of scatter. There is a considerable amount of scatter, but this is the line that we draw intuitively, and we can see that most of the failure points lie above that line. Most of the failure points lie above that line. Some points lie below that line also, but most of the points lie above that line. So had we used that line as our design criteria, it would have been most probably on the conservative side. So had we done this maybe 110 years ago, we would have been stars, you can say. But unfortunately, someone has already done that. Okay? And this line is called the modified Goodman line. Okay? And this criterion is basically the modified Goodman failure criteria. And obviously, we have just seen the experimental results. So experimental results show that this design is most probably on the conservative side, but we still use it because one, obviously it is conservative, so it's not a problem, and second, that it's analytically it is easier to use. Later on you see some other criteria as well, okay? But analytical, they are a little bit more difficult than that, okay? So at the start we would maybe rely on this modified Goodman criteria, and then in the next lecture we can maybe see the other criterions as well, okay? Now so so that means that in any stress situation you are given, so what does this criterion mean? So first you calculate the sigma A and sigma M, obviously using the fatigue stress concentration factor. And then if you, on the figure, if you do this by obviously using equations, but on the figure, if you see that if that point, if you plot this on this figure, and that points come somewhere around here, so that means it is safe. Okay? If it lies here, it is safe. If it lies here, it is safe. But if it comes out, if you plot that point and it comes out here, so that means it fails from the fatigue point of view. Fails means for infinite life. Okay? It fails for infinite life. So this point, if the sigma A and sigma M combination are such that the point lies here, so that means the part would not have infinite life. Obviously, it would have some finite life, and we can calculate how many number of cycles would that part endure. Okay? So that we will also see later. But at the moment, we are considering for infinite life all the points that lie inside this region. Okay? So they are safe. Okay? And all the points that lie outside, they are they would be failing from the fatigue point of view. Now, obviously, I draw this figure again. There is another problem of yielding. Okay? So as you are increasing the mean stress, okay, there would be a point where the material would start yielding. Okay? Now, how to take care of that? We take care of that by drawing a line that we call the yield line. Okay? So if this is SE, obviously SY would be larger than that. Okay? So at when sigma M is equal to 0, if you are within SE, there is no chance of going over SY. But for obviously for sigma A is equal to 0, this is static test. static case, so obviously we have to consider yielding. Now for combination of these two, what we can do is we can combine these 2 points. Okay. So with a line. Okay. So this would give us the yield line, and this is also called the Langer line. Okay. So this is the modified Goodman line, and this is the Langer line. Okay. So now there is a region here. Okay. That is from fatigue point of view. So if I calculate a fatigue safety factor, so that would be greater than 1 for this region, but the yield safety factor would be less than 1. So when we are designing for fatigue, we also have to check for yielding. Okay. So first we can check for yielding. So that means that would mean either our part fails in the first cycle yield or it doesn't fail. If it doesn't fail, then we can check for fatigue. Okay. Just to reiterate, I can maybe, this is point A, this is point maybe B and C. Okay. So in this region that I have delineated by blue color, B, C, S, Y, I can say. So this point, and this point. So according to this figure, this point you would have no yielding, but also no infinite life. Okay. But we will have some finite life for fatigue, and we can calculate what is the life of that part. Whereas for this region, okay, A, B, S, U, T, okay, you have yielding. Okay. So in this region, if your stresses combination sigma A and sigma M fall in this region, then you would have most probably yielding. Okay. So obviously we cannot use this region. So this is safe for infinite life, and this region indicated by blue is safe for some finite life which we can calculate. And this line CB, so for example F is point carried, so this line is called a modified Goodman line. And here just a point that although this is called a modified Goodman line, even if I say a Goodman line, or in the exam or in the book somewhere it is mentioned a Goodman line, it still refers to this line. Okay? Original Goodman line is not used anymore. Okay? So interested students can look at what was the original Goodman line. I don't want to confuse you, but remember that whenever in this course or in your book you are talking about Goodman line, so that would be this line, the modified Goodman line. Okay? And the yield line is called the Langer line. So any questions? So now, so all of this discussion was valid for sigma m having a positive value. Okay? For this graph, we only showed sigma m having some positive value. Now, what happens for sigma m less than 0. So as I said previously, intuitively we have also talked about the residual stresses, that when you have the compressive residual stresses, generally you have better fatigue life. So we can estimate that fatigue sigma m less than 0 would generally be better in terms of fatigue, and the tests also indicate that. So in this graph you can see that this part shows when the mean stresses are negative, compressive, and this part shows that when the mean stresses are positive. So when the mean stresses are positive, the effect is negative. So you have reduction in fatigue life, whereas when the mean stresses are compressive, the fatigue life is better. So if we are talking, for example, on this curve, on this graph, and if I just extend this to this portion, so when sigma m is less than 0, so that what that graph is basically showing, that the test results indicate that this failure basically continue like this. So fatigue life basically improves as we go into the negative region. The compressive mean stresses generally improve the fatigue life. You can increase the alternating stress even from SE, and this is what we said here. And that is actually verified by experiments, that when you the negative mean stress, the life of the part improves. But the convention is to be on the conservative side. We ignore this positive effect. We ignore this positive effect. So this is sigma m, this is sigma a, and now this is the region where sigma m is negative. So previously we had this failure criterion. So this is SUT and SE. So I have not drawn the Langer line. Obviously there is also Langer line here. So as you go into the negative mean stress region, so when the mean stresses are compressive, so they are better from the fatigue point of view. So it could be that we could extend this line something like this, or maybe some curve. But to be on the conservative side, the convention generally is to ignore this positive effect and take this line as a constant. So we take this line at SE level. So that means basically when sigma m is less than 0, we ignore the positive effect. So the result is same as sigma m is equal to 0. That means sigma a is fully reversible. So whatever we discussed previously for completely reversed load is also valid for sigma m less than 0. So only thing that would be not different, we also did the first cycle yield check. So that you still have to do. Obviously as you have SY here, so you also have SY here. So we have to check for yielding also in compression. So this would be your this would be the total region which is safe. This in compression and this in tension. I can have the diagram in more clear fashion. So we can ignore these equations. We will move to them later. So this is the modified Goodman diagram. That is also been drawn for the compressive region. Okay? So in tension, you connect SE with SUT on sigma M and sigma A axis. Okay? And also you have this Langer line SY. Okay? And similarly, on the compressive side, we don't take the positive effects of the mean stress. We take still sigma A as SE, and then we also have the Langer line on the compressive side. Okay? So this A, B, C, D, E is actually the safe region. So if your stress combination, and we are talking about SE here, okay? So for infinite life. Okay? So for infinite life, this is the safe region. If your point lies somewhere inside, then that means it will have infinite life. If it lies outside, then it would not have infinite life. So any questions from the previous discussion? Okay, and by the way, this diagram is called the augmented modified Goodman diagram. So augmented means that we have extended this to the compressive side. Okay, now what happens for finite life? Okay. Finite life means that for your any combination of sigma A and sigma M lies somewhere here. Okay. Now what we can do is similar to this as the Goodman line we used, we can draw another line, okay, that passes through this point from SUT, another line that passes through this point and comes here, okay, and that value would give you the value of fatigue strength for completely similar to a completely reversed load. Okay, so obviously at this point the load is not completely reversed. Okay, so for which stress to aim for, either we can aim for this strength value, okay, or this strength value. Okay, so the better method is to, similar to the Goodman line, we can draw another line that moves from SUT and passes through the point combination of sigma A and sigma N, and then we extend it to sigma to this line where sigma M is 0. Okay? And that would give you the fatigue strength, okay, or the reversible stress. Okay? And then we can, for that fatigue strength, we can use this formula to find out the number of cycles. Okay? So it will basically convert this into sigma reversible, and that is equal to this fatigue strength, and that can give you the number of cycles. Okay? Or we can go in the other direction also. If we are given that we have to go for 10⁴ cycles, so we can find the fatigue strength for that and plot it on this curve and then join it to SUT to find the region which is safe for that number of cycles. Okay, so if you join it with endurance limit, you are producing a region that is good for infinite life. And if you are joining it for some other fatigue strength value, so maybe for a 10 raised to power 4 cycle, okay, so at 10 raised to power 4, so that means that you are drawing a region that is safe for 10 raised to power 4 number of cycles. Okay? So you can, any combination of sigma A and sigma M that lies inside this would be safe. Any combination that lies outside this would obviously be unsafe. Okay. So okay, so last is the fatigue factor of safety. So how do we define what is the factor of safety when we are using this, for example, Goodman criterion? Okay. Once again, okay, so if for example you have some combination of sigma A and sigma M, and that point lies somewhere, for example, here, okay, so I can call, so this is sigma A, this is sigma M, and this point is Z. Okay. Then how to define the fatigue safety factor? So fatigue safety factor is generally taken as the extension of this load line. Okay. So if I extend this load line, okay, and it would meet this modified Goodman line at this point. So this point maybe I can say is point R. So the fatigue factor of safety would be OR divided by OZ. Okay. So that would give you the fatigue factor of safety, and the yield factor of safety would be to extend this line further and meet the Langer line. So at point S, so yield safety factor is OS divided by OC. So if fatigue factor of safety is less than 1, so that means that we are in this region and we would have some finite life, not infinite life. And if yield factor is less than 1, obviously then your design has failed because it has yielded in the first cycle. Okay. And once again, if the point lies here, so we can extend it to find SF, and because means SF means stress is 0, so we can replace it with sigma reversible, and then we can use the SN diagram, okay, to find the, for that reversible stress we can find the number of cycles to failure. Okay.